Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 151, I chat with Jim Venable and Alan Ruberg of the Wireless Speaker and Audio Association about the next generation in wireless audio. So stay tuned.
Netcasts you love.
From people you trust. This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded March 11th, 2013. Episode 151, Wireless Audio That Works. This episode of Home Theater Geeks is brought to you by Manpax, manly goods on a schedule. Get started today and have underwear, socks, toiletries, shaving supplies, and more delivered to your door. Visit manpax.com/twit and get $10 off your first order of $30 or buy a $50 gift card for $40. Hey there, Scott Wilkinson here, the Home Theater Geek. This week's guest geeks are Jim Venable, the president of the Wireless Speaker and Audio Association, and Alan Ruberg, the chief technologist of WiSA. And we're going to be talking about, obviously, wireless speakers and audio. Hey, Jim and Alan, welcome to the show.
Thanks.
Hey,
Thanks
Scott.
for having us.
Thanks a lot.
We're so glad that both of you are here. Now, those of you who are tuned in to the live stream at live.twit.tv or logged into the chat room at irc.twit.tv can post questions for Jim and Alan, and I will pass along as many as I can. Now, I wanted to start out with the whole notion of wireless audio. It's been around for a long time, but it's gotten kind of a bad rap. Give us a little sense of the history of wireless audio and why has it not performed any better than it has?
Well, you know, wireless audio that's been used so far in the home environment is really operated off of the Wi-Fi space. And as we know, Wi-Fi has become very jammed with lots of other devices, you know, microwave ovens or baby monitors or security cameras or just whatever. And so this really creates a lot of competition for that bandwidth. And trying to transmit high-definition audio over that bandwidth is problematic at best. You have to compress, you have to decompress. There's lots of challenges with getting high-definition audio to work. So hence, those products that have been brought to market working in that space have historically not really provided the user experience that the consumers are looking for, and so
or the quality audio that some of us anyway are looking for.
Absolutely. I mean, you can't transmit 24-bit, you know, 96 kilohertz on the 2.4 gigahertz Wi-Fi space. It just doesn't. You just can't get there from here.
Yeah, there's not really enough room. This might be a good time to put up the visual of the 2.4 gigahertz spectrum.
Sure, let's take a look.
Yeah, let's take a look at that.
Because there it is, in fact.
Yeah, so
tell us what we're looking at here.
Okay, so on the horizontal axis, this is the 2.4 gigahertz Wi-Fi channels. So you can see them 1, 2, 3, whatever, to 13. And each of those humps there is one N 802.11n stream, and the height is the amount of power it has, and then each rectangle that's going on through there is a different network. So we probably have around 100 networks here, maybe even more. This is at a trade show, and this is
oh well, that's gonna be pretty crowded at a trade show.
Done some demoing, yeah. But
anybody who has gone to CES and tried to get a Wi-Fi signal has noticed how difficult that is.
Right, and this is why you can't.
Yeah. Okay. Now we see a visual representation of why you can't get on the damn network when you're at CES or any other trade show for that matter.
Pretty much any other one either. That's right.
Yeah. So
okay, so we got like 100 networks competing for that particular bandwidth, and let's make sure everybody understands that when we're talking about 2.4 gigahertz, that's a particular frequency, but really we're talking about a range of frequencies, right?
Yeah.
Yeah, absolutely. And there's 13 individual channels, but those channels haven't been used alone since the 90s. So they've always been paired up with 802.11g and 802.11n, which are the modern versions of this that we use now. So I don't know if you recall, 802.11b was only able to do, what, 10 megabits a second or something like that. And then
sure, I do remember that.
B doubles that and N doubles that again. So, so every time you do that, you have to use more channels. So use pairs of channels or 4 channels in a row. That's why there's only 3 humps in the image.
Gotcha. Okay, so what's a poor wireless audio signal to do then?
Well, go somewhere else.
That's kind of what I figured. Okay, so where can we go?
Okay, so some people have noticed maybe that there's this 5 gigahertz band that's available, and if you get a dual, what are they called? Dual
Band router?
Dual band router, exactly. Then it supports this 2.4 gigahertz for people who have more primitive devices, and then some laptops will have this 5 gigahertz capability as well. But for example,
isn't one of the 802.11 standards? I mean, there's A, B, C, N, G. Isn't at least one of them operating in the 5 gigahertz range?
Yes, yeah. The 5 gigahertz range pretty much started with 802.11a, which got because it wasn't as because you needed this dual band router. 802.11g really did win out to A. The other thing about the 5 gigahertz spectrum is it doesn't go through walls very well.
Oh, that's right. The higher the frequency, the less capable the signal is for transmitting through walls and so on.
Exactly.
Yes.
We see this quite a bit with the wireless, one of the wireless HDMI, not to use an official term, but one of them, I think it's wireless HD or WHD, I forget which one, uses 60 gigahertz.
That's right.
And it cannot go through walls at all.
That's correct. It's wireless HD is at 60 gigahertz, right? Transmitting video, I believe.
Correct.
Yeah.
Yeah.
So anyway, so at 5 gigahertz, you're less able to transmit over long distances and through walls, certainly.
That's right.
Exactly. But that's really not such a big deal for wireless audio, especially if you're working in a single room or in a single house. In a home theater environment, really all your speakers and your transmitter, what have you, are all in more or less the same room. They might be in cabinets and what have you, but that has little to do with the reception.
So the 5 gigahertz band rather is less crowded. I think we have a picture of. I'm sorry.
Right. So yeah. So before we get to that graphic, you know, we're still talking about Wi-Fi in the 5.0 to 5.1 gigahertz. We still talk about Wi-Fi in the 5.8 gigahertz. And we're going to show you a graphic here in just a second where we're talking about, okay, well, what's between those two? And if we put up the
uniband
graphic.
Yeah, there it is.
Then you'll see that on the far left side, that's what we're talking about Wi-Fi. It's still pretty darn crowded. And way up the right-hand side at the 5.8 or so, 5.7, that's pretty crowded, and that's also Wi-Fi. But in between, you see this valley where there's not much going on. That's where the WiSA technology plays. So we're talking about a pretty wide spectrum of channels, about 24 of them, where wireless audio can reside without any interference, and it enables to transmit and receive 24-bit up to 96 kilohertz uncompressed audio.
Holy smokes. That's some serious, you need some bandwidth for that.
Yeah, it's 8 channels at 96 kilohertz. I believe it's 36 megabits a second.
Wow, that's pretty significant.
Yeah.
Now, Ibda bloke in the chat room is asking, why not do spread spectrum or frequency hopping to achieve, to cut down on interference?
I don't know the exact answer to that. I do know that the developers of this technology started with ultra wideband, and which is basically a spread spectrum technology, and it didn't work out for them. One of these days I have to remember to ask why that is. But for
yeah,
the
I'd be curious.
Yeah, but for the 5 gigahertz band, what we haven't got to is that part in the center that didn't have so much traffic. There's a requirement for dynamic, by the FCC, called dynamic frequency selection. And that starts around channel 52 and goes up to channel 140, that part in the middle. And the FCC, or whatever regulatory commission you have internationally, demands that inside that spectrum, if you see energy from radars, the transmitter actually has to move channels. And
you mean like radar, like as in, you know, military radar,
or weather radar,
weather radar. Okay, all right.
Yes, yes. So if it detects that, then it has to move channels, and there's lots of channels in there to move.
How wide are each of these channels? We're talking about specific frequency numbers, but really each channel has a bandwidth of its own, does it not?
It does. It does. These are 50 megabit channels, basically.
Megabit or megahertz?
Megabit. I'd have to look at the chart again to see how many megahertz it is.
Oh, I see. Okay.
Yeah.
So each channel can accommodate up to 50 megabits per second?
Yeah, it's 20 megahertz.
20 megahertz bandwidth of frequency.
Right.
But it can accommodate up to 50 megabits per second of data.
That's right.
That's a fair amount. I mean, you could, I mean, even Blu-ray, coming off a Blu-ray is less than 50 megabits. The video is like 30 something, and the audio is much less than that. So you could even potentially do wireless HD transmission along these lines. But of course, you're only doing audio, and you're doing 8 channels of 90 up to 9624 uncompressed, and that's a very important point to make.
So one of the cool things about this technology is that, so you got these 24 channels that you have available to you, and the way this technology is architected, it always is looking forward and locating and identifying a channel that is interference-free. So that if on the odd chance that you have, you detect some sort of interference on the channel which the signal is residing, then it already knows where to go. And everything moves at once. The transmitter and the receivers, or the Blu-ray player and the speakers, all move at once without any loss of data, and it's undetectable. So you always, and then once it gets to that new channel, it identifies the next channel that's interference-free, just in case that it would run into some more interference. So it always knows where its new home is going to be, should the occasion arise that it needs to move.
Well, that was one of my next questions, was if it has to move, isn't there likely to be some sort of gap in the transmission?
No, because what happens is that the entire system knows when to move simultaneously. That's the first thing. The second thing is that there's basically 5 milliseconds of buffering in there, and the switch can happen within that 5 milliseconds. So it can actually be done without any artifacts at all, no clicks, pops, gaps of any kind. So this is something that's completely transparent to the listener, and you just don't hear it because everything has to happen at once. Going back to the bandwidth issue, you're really not allowed to use all that bandwidth. For one thing is that we're talking about radio, and radio's is pretty flaky, and it needs to you need time or additional data to do error correction on it. So actually 1/3 of that 36 megabits I was talking about is only for error correction.
Oh, wow.
Yeah, and then the rest of the time that was there is the time that the system goes silent so that it can detect the radar.
Huh. Well, but what do you mean go silent? I mean, if it's transmitting data, it still has to find that radar signal, right?
Right. So what you can observe is that we're only using 36 megabits a second. So the idea is that in that 5 millisecond interval, all the audio data goes at once. Okay, and then there's a gap.
And gets accumulated in the buffer.
Right, and then there's a gap, and during that gap, you know, the transmitter has to go silent in order to actually hear the delicate radar signals coming in.
Are they that delicate? Are radar signals delicate? I didn't think they were. I thought they were pretty robust.
Well, anything at a receiver side is going to be a lot quieter, as it were, than where it started out.
Well, that's true.
Right. So, and you're, I don't know, 15 miles from the radar, and so you really have to listen hard. You know, it's like trying to listen to somebody talking across the room while somebody else is shouting in your ear. It's the same thing.
Yeah. Okay, so we're talking about buffers and transmitters and receivers. How is an actual physical system going to manifest itself? What does a WiSA system need in order to function in this way?
Okay, so here's an example of a amplifier. Okay, I'm trying to get this close enough.
Yeah, raise it up a little bit. There you go.
There you go. Okay, this is an amplifier. This is your typical 100-watt amplifier that you might see in a car stereo, or is actually built in as a module into your AV receiver.
Okay.
And this one's actually designed to mount in the back of a speaker. So this is the back plate. Okay, get the lighting right. This is the back plate of the speaker, and then the power connection's right here. Mm-hmm. And you would have, pay no attention to this connector. That's just because of the developers. So this is a typical amplifier, but this would be for a powered speaker arrangement. It could just as easily be put in a box and then put next to the speaker. Mm-hmm. So it doesn't have to be built in. Now, the entire wireless system for the speaker is on this little card right here, and I'll give you a better example of that in a moment. Okay, so just this little piece right here is everything you need to
the topmost card in what we're looking at here.
It's a receiver module.
Yeah. So that's the receiver module for it, and let me get you a better example of that. Okay, so here it is, all on its own. And you can see kind of relative to the size of my hand, it's not very big at all.
Right.
Well, we've got big light here. Okay, there you go. And the gold pieces in the corner are actually the antennas.
That's what I was going to ask you next, was what about the antennas?
Yeah. So
there they are, just four little pieces of copper or gold or whatever.
Yep. And they're enough to listen if you're going through, say, a wood case. If it's an aluminum case, then you've got to actually put connectors on this and then do some fancy work, similar to the iPhone, where you have the antenna that if you grab it, the phone.
Oh yeah.
But
that was in the iPhone 4, not. I think they solved it maybe in the 4S and the 5. I haven't heard as much of it.
They did, but it's a similar kind of. Those are patch antennas that would go out. It's not that they're not reliable. It's just that those are the kind of antennas that you would have like sitting on the outside of a metal enclosure.
Right. Now, there aren't that many speakers that have metal enclosure, but there are a few. So it's something that...
Some notable manufacturers, actually.
Well, like the really popular powered JBL speaker that are used in a lot of professional monitor installations for like...
Oh, I didn't realize that.
Yeah, those are metal.
They got to be able to be dropped, yeah.
Mm-hmm. I do know that who made the is it Krell, I think, who made some all aluminum speakers, or Macintosh, I think. But those are very high end.
Right.
Well, Bang Olufsen does a lot of aluminum. Yeah.
That's right. That's right. Okay. Sorry to interrupt. Go right ahead.
No worries. So anyway, in general, this is this little module. It doesn't cost very much. It's not very big, and that's what goes inside the speaker. Mm-hmm. Now, the transmitter. So anyway, this has, I don't know if anyone's familiar with diversity antennas, but your Wi-Fi router, if it has a bunch of antennas on the back, part of that is put together so that if your signal is weak going into one antenna, then if you were to move over yourself, then the signal will get better. But instead, on the access point, the router, the Wi-Fi router, they put 2 antennas, so it just measures which one's better, so you don't actually have to move over a little bit. So this guy's got 4 antennas on it. Okay, up, down. Yep. I can't work backwards here.
Yeah,
okay,
right. No, it's fine.
It's got 4 antennas on it, and that way, if it'll pick whichever antenna has the greatest signal at that moment. Okay,
now this is the transmit. This is the transmitter, right?
This is the receiver.
Oh, the receiver. Sorry. Yes. Okay.
Yes. So that's quad diversity. The transmitter only has a single antenna.
Of course.
However, I'm going to change what I just said in a moment. So this would be this is the antenna that runs the system. You know, so this is what transmits all the digital audio, and it would go into a faceplate for an AV receiver or a dedicated switch box or inside a television or next to a television, what have you. So this is the transmitter antenna.
Now that looks like a square of copper or gold or some.
Yes, exactly, and that's perfectly fine antenna. So if you get, again, an access point router, wireless router, that doesn't have antennas on the outside, it uses this style. It's called a patch antenna.
Now,
okay.
The antenna, the size of the antenna, as I understand it, is related to the wavelength of the frequencies that are being transmitted and received. Is that right?
Exactly so.
So these antennas, how do they relate to the wavelength of the radio frequency or RF signal that's being transmitted and received?
Well, 5 gigahertz is only a few millimeters.
Few millimeters, okay.
Long. Yeah.
So these antennas are a few millimeters in size, roughly.
Right.
So that corresponds with that wavelength. Okay, just curious.
No, but that's exactly it. So these antennas are actually, they might just look like squares, but they're actually fairly carefully designed, or else they don't work so good.
Yeah, gotcha.
You know, you think of antennas as being these long stick things, and you know,
right.
They're somewhat miraculous. So you might notice that there's a second antenna here. I don't remember.
Yeah, I was going to ask about that. Yeah.
Right. Well, that's the radar detector.
That's not a transmission antenna; it's a radar detector antenna.
Right. So do you have the graphic, which is the radar? It's got clouds on it, little clouds. And
I don't think so. I don't think I have that one.
Okay. So the way this works is we talked a moment about having all this data come bursting in and then having a moment to listen. And so both antennas are actually used for that. So one antenna is listening for the channel that the system is currently on to see if there's interference that would cause it to move. The second antenna is listening for the next channel to go to. So the requirement for this crazy band in the middle that we were talking about that has to do radar detection is that you're not allowed to occupy a channel until you've waited 1 minute.
Until it's been quiet for 1 minute.
That's right. And then if you get kicked off, you can't go back for 30 minutes.
Wow.
So yeah, so there's these crazy rules. And the 1 minute rule is the thing that drives the computer networks completely mad. Because you would actually have to cut down bandwidth while you were sitting and listening and searching for a next channel to go to and waiting your minute and maybe going to a hostile channel. So this isn't great. I mean, computer networks operate there sometimes, but it's not great for computer networks, at least if they're compliant.
I was going to ask you about that because you said Wi-Fi in the 5 gigahertz range is usually in the 5.1 and 5.8 range.
Yes.
Are there actually Wi-Fi devices that operate in this middle ground that we're talking about?
Sure, they're allowed to do that. And the system was actually designed for 802.11a because the Europeans were sick and tired of 2.4 gigahertz. And so they wanted to have a new home. So this 802.11a came along. It was 5 gigahertz only. And then they still only had, I don't know, 4 or 5 channels. And they wanted more, so they came up with this DFS thing. They asked the military very nicely, well, can we use this if we're not interfering? And they came back and said, okay, you can do that. And
here are all the rules.
Under these conditions, yeah.
Goofball rules. And So yes, it is possible. We just got back from Europe, and there were very few networks that were running in there. But there's all this handshaking and weird stuff that has to do. So you're not going to get the full bandwidth all the time with that. So if you're doing a long streaming thing like a video or something, and you lose your network, you either go into the 5.1, 5.2, or the 5.8. You know, while you're waiting for that new channel to become available.
So that really, Scott, makes the case for why we believe that you're not going to see the same crowded conditions in this UNE band or DFS range that you will see, that you have seen in the 2.4 and you are beginning to see in the 5.1 and the 5.8, because it's just really not conducive to run laptops or that kind of a Wi-Fi or internet access experience in that space. You just can't handle it.
Got it. Got it. And that makes a lot of sense, actually, for you to put wireless audio in that range, if you can solve the problem of having to jump around if it detects radar and so on. Tell us what UNE and DFS stand for, just so we make sure everybody understands.
Okay. UNE means unlicensed, oops.
Sorry to put you on the spot there.
Unlicensed national information infrastructure. Right. Okay, it's a very U.S.-centric term, actually. So the propeller heads just say 5 gigahertz, and that really does. It's not quite all the way down to 5.0 gigahertz, and it doesn't quite go to 5.9 gigahertz, but still, it's just 5 gigahertz. You were commenting that 2.4 gigahertz is a bunch of channels, right? Well, you know, the 5 gigahertz band is very wide, has 24 channels in it.
But the real differentiator is DFS, that dynamic frequency selection, and that's what really sets it apart from you know, the 5.0 and 5.1 and 5.8. It's this notion that you have to be dynamic. You got to be able to go from one channel to the next, depending upon what other activities that are happening in that bandwidth, vis-a-vis the radar interference. Right,
exactly. Got a couple questions in the chat room. Oh, sorry, did you have another point you wanted to make there?
No, it's okay, please.
Okay, let me get a couple questions in here from the chat room. Nerve asks or comments, I see one small problem with this, if I'm following it correctly. Where is the digital to analog converter, and what kind of quality is it? And I would ask the same question about the analog to digital converter. I mean, presumably, actually, these days, a lot of audio starts out as digital. You download it or rip it from a CD or whatever. So it stays in the digital domain until it finally gets to the speaker. Do you guys have anything to say about digital to analog conversion, or is that up entirely to the manufacturer of the product?
Well, it's completely up to the manufacturer of the product. The transmission of the audio is always 24-bit. Now, that may not be always full, depending on what the content source is. So much video, like DVD video, the audio for that is generally 16-bit. Right. After it's decoded. So there'd be a bunch of bits that are more or less unused, unless you have some kind of advanced processing in your receiver. So that would generate more bits. But in general, until you get to Blu-ray, you don't see a lot of 24-bit content. As you observe, the digital and analog converters are close to the speakers, which is actually pretty neat. Because it brings in a few things. One is that you have the opportunity to pull the professional speaker trick of having your amplifiers exactly matching the speakers. Okay, so you have that amplifier right there, and the signal goes right up to the edge of the amplifier where the digital analog conversion is done. Certain types of Class D amplifier doesn't mean digital, which is, you know, many things are Class D amplifiers right now, but and people mistake that it means digital, but there are directly converting digital amplifiers, and actually the one I showed you is one of those, in that it has a chip in it that directly converts the digital audio signal into a pulse width that then goes into the speaker. Which actually together kind of act like a digital to analog conversion. Other type of amplifiers, such as the ice power amplifier, require a digital analog converter in them. It's still a Class D amplifier, but operates in an analog input mode. So that's a lot on Class D amplifiers. Hopefully,
no, that's fine. That's fine.
But
it actually brings up the question, though, of a WiSA system that implements the WiSA wireless audio standard, and I want to talk about the fact that it is a standard. But such a system basically would need active speakers, or that is an amplifier near or built into the speakers in order to operate, right?
Yes, that's right. Otherwise, the point of wireless is kind of defeated. Now, okay. Well,
I must admit, I'm a big fan of powered speakers. I think that the idea of building an amplifier into the speaker and optimizing that amplifier for that speaker is really an excellent idea that happens all the time in the pro audio world. And I've always been a little curious why it doesn't happen more in the consumer world.
Well, I think it's a new thing, and we're seeing it creep into the consumer world. It means that your speakers look like they're more expensive when you get them, but
and probably are more expensive because they have some electronics in them.
Yeah, but on a system level, it only looks like it, because what you're doing is you have the opportunity to eliminate the amplifiers from your receiver, for example, or from your or if you have separate, amplifier blocks or something like that, they would be near or in the speakers instead.
Right.
So the system cost is probably roughly the same. My experience also with power speakers, and this may be yours as well, but boy, they sound nice because of the ability to tune the amplifier and the speaker directly, and then having local DSP for doing electronic crossovers. And in the consumer world, electronic crossovers are incredibly hard to deal with. They're very expensive. It causes so many more amplifiers. It's just a mess. So nobody uses them, and we're stuck with passive crossovers, which are necessarily imperfect.
Right, exactly so. Well, I've got several other questions in the chat room and some more of my own. So if you'll just hang on 1 second, I do want to take a moment to thank our sponsor for this episode, which is Manpax, manpax.com. Now, as a guy, and most of our listeners are guys, it's not so fun to go shopping for your basic stuff, your underwear, your socks, your shaving stuff. It's really not a fun thing to do, and there are plenty of other things to do that you'd rather be doing rather than that. Well, manpax.com offers a great solution, and that is to order what you need online, and it'll come to you every 3 months on schedule without having to do anything else. And you can modify that order at any time and get what you need delivered right to your door without having to go out and shop around or even, cruise around the web. I took a look at the site myself. They even have, the underwear and socks that I wear. So it makes it super easy for me to deal with that particular chore in everyone's life. It's a start it, stop it, change it anytime subscription for all your basic essentials. You can manage your account, and they remind you before shipments are sent out, so there's really no surprises. You can update your next pack if you need, or just wait for it to come to you. There's free shipping, free returns, easy account management. The customer is always king. Now, there's an offer for our listeners and viewers. 2 exclusive offers, as a matter of fact. You can get $10 off your first $30 order, or buy a $50 gift card for $40. All you have to do is go to manpax.com/twit and get started today. And we thank Manpax very much for their support of Home Theater Geeks. Okay, now let us talk about, let me get another couple questions in before we talk about the standardization of what you're doing here, because I think that's a really important thing. Titus asked a little while ago about the antennas. Are those tiny phased array antennas?
At the moment, they're not. They're simply diversity antennas. Only one is used at a time, but the radio monitors which one has the greatest signal strength and picks one. There is nothing stopping it from being a phased array antenna and getting some more gain out of it. So that's a place where the system could improve.
Mm-hmm. F-Loop in the chat room asks, oh, sorry, did you have something to add?
No, not.
Okay.
No.
F-Loop in the chat room is asking, one hard part of this problem is synchronization of multiple speakers to near microsecond differences without introducing other problems like jitter and so on. How does WiSA solve this problem, and what specification are you trying to achieve in this regard?
Okay, there's a couple numbers associated with that. The first, well, so the thing that really gets all of the speakers working at the same time is that all 8 channels at the moment are being broadcast in the same packets together. So the speaker is the thing that says, okay, well, this is the channel for me. So it's not like it's a unicast to each individual speaker. All the speakers get all the data. So the speaker-to-speaker difference in time is at most 160 nanoseconds.
Well, that's certainly under the threshold of human detection. Yeah.
So, and then we brought up another number a little earlier that I should describe, and that is this 5 millisecond latency in the system, which is basically used for buffering and error management and those kinds of things.
Right. They get 5 milliseconds worth of data into the buffer at a time, and then the system waits and listens for radar and so on, and then sends the next 5 milliseconds and so on.
Right. So with a typical over-the-top system, for listening to radio over the internet or some in-home systems, you've probably seen in a website, like if you're watching YouTube's a video example, but it'll say buffering when it first comes up. And what that is it's giving the network enough time to be able to recover, in case that there's some kind of data loss. So that is however much time it uses to buffer is as much time as it can hide when the signal's lost. Okay, so with a lot of over-the-top audio systems, especially that run on the internet, that could be 5 seconds of latency.
Certainly well above the threshold of human perception.
Right. So synchronizing that with audio, with video, is really a problem.
Yeah.
And then, but I would say that a really good in-home, up until this point, a really good in-home audio networking system might have, 30 millisecond or higher latency, which makes it makes it a little harder to do video synchronization, but more importantly, you don't get the immediate feedback like if you're doing gaming or anything that requires like some kind of interaction with the television.
Right.
So
now,
5 seconds is gaming quality.
5 milliseconds, you said.
Yeah.
Okay.
What the system is doing. Yeah.
And it wouldn't have a problem then with video lip sync or anything like that either.
No, not at all.
Yeah.
In fact, one of the problems we have is that every now and then we get some of the prototypes are very basic, and some AV receivers have the ability to actually adjust the display latency, but some of the boxes we've worked with these transmitters in the early days don't have that adjustment in it, so that sometimes the TV is between 30 and 60 milliseconds behind the audio. So we have inverse lip sync problems.
Yeah, indeed.
So we actually have to slow the system down in some cases. So we switch our TVs to game mode and everything syncs up.
Got it. Jim, why don't you tell us a little bit about the standardization procedure?
Sure.
What is WiSA hoping to achieve in terms of creating a standard that, and how hopeful are you that manufacturers will fall in line and use it?
Well, what really started all this was the fact that the DTVs are getting thinner and thinner, and that the audio quality coming out of them is just going down in proportion to the thinness of the TV and the quality of the video.
I totally agree with that.
Yeah, and so the consumer, they've gone out and they spent a couple grand on this big, beautiful display, and they, hung it up on the wall, and they turn it on, and, the audio is terrible. And so what they're looking for is an audio experience that matches the quality of the video experience that they have in the home. And because of the architecture of this technology, and because of what's going on in the marketplace, we believe very strongly that we are at a market inflection point where if there was a quality audio wireless technology available, that the consumers would embrace it, provided that it lived up to its expectations. And living up to that expectation, I think, is the key component of what the WiSA Association is all about, and that is guaranteeing that wireless interface between that DTV or the Blu-ray player or the set-top box and the speakers, guaranteeing the quality of that wireless interface, so that when they go out, and interoperability is also very key, so when they go out and buy that brand X TV and brand Z set of speakers that are WiSA compliant, they got the WiSA logo on it, they bring them home, plug them in, turn them on, it's just going to work. So it's kind of analogous, and I say this to folks I'm talking to, because then they kind of realize what I'm saying is it's analogous to the Wi-Fi Association. Back in the early days when they just started experimenting with putting out products in the 2.4 gigahertz bandwidth, and they brought them home and plugged brand X with brand Y, it didn't work. And so the industry in general got together and formed the Wi-Fi Association, so all these different manufacturers could standardize on the same specification for the wireless interface so that their product can work with the other products and vice versa. So we're doing basically the same thing with home audio, because we know that we only have one shot with the consumer. They've been down the wireless speaker path before. They didn't like it. It didn't work. So we have to make sure that those companies that are manufacturing products based on this technology go through the compliance testing procedure, get certified so that their products work with other products and that they meet the spec for that wireless link, giving the consumer that assurance that they're going to have that quality experience that they're looking for to match that display.
So you mentioned the certification process.
Right.
This makes a lot of sense to me, that if anybody who wants to put the WiSA logo on their product needs to go through a certification process. Well, tell us a little bit about that process.
So when a manufacturer becomes a member of the WiSA Association, they get access to the certification test specification. And from that, they take the requirements and build it into their marketing requirements document that goes on to engineering documents, that goes on to building product, that eventually goes to market. And they'll get to a certain stage in that development cycle, engineering sample, where they will send the lab, our lab, a SKU that they plan to take to market, that we will take it through the testing procedure and certify it compliant with the spec. Now, we're not a gotcha organization. We want everybody to pass. That's why if you're a member, you get the spec, you know exactly what we're going to do, exactly what we're going to test for, how we're going to test it, so that you can make sure that product is going to be compliant. So we'll run it through the lab, we'll stamp it as certified, then the manufacturer is licensed to affix the WiSA logo and go to market.
You know, this reminds me, I don't know if you're familiar with the, in the professional audio, more in the musical instrument end of the professional musician market, there was a standard called MIDI, Musical Instrument Digital Interface.
Right.
This reminds me something of that. Because here were all these competitors who were making synthesizers in that particular case, who got together and said, we need a way of interoperating one of our devices from one of your devices and being able to hook them up and share performance data. And so MIDI was born, and that was 30 years ago, and it's still being used today.
Right.
So
that's a really good example, Scott, and I wish I had thought about that and picked that one, but that's probably a more appropriate example, actually. But that's exactly right. And, you know, the speaker manufacturers, they've got to know what the transmitting emitter manufacturers are going to emit so they can make sure that they link up and it all works. And this is exactly what we're going to do. We're going to spell out, and we have spelled out very clearly what that requirement is. We've already released our 1.0 certification test spec to our members, so they've got it, and they're all working towards product that meet that specification.
Beatmaster in the chat room is asking, who are the members of the WiSA Association now?
So we've got about 15 or 20. They range from technology providers, Summit Semiconductor, Silicon Image, the ODM. We have 3 ODMs, Hansong, GGEC, and Meiloon, who manufacture about 90% of the AV products for the brands. We've got a number of brands: Klipsch, Polk, Definitive Technology, Bang Olufsen, Dolly,
Paradigm,
Martin Logan.
Pretty high-end brands.
Yeah.
Yep.
Yeah, and the list goes on.
Well, and then also more on the transmitter side, there's Sharp and Pioneer as well.
Oh yeah, Sharp and Pioneer represent the consumer electronic side. So we got a really balanced, ecosystem out there. Those that will, do the transmitting side, and those that build the brand receivers or the speaker side. So, and then we'll have accessory manufacturers that will build, wireless hubs that can be used with legacy TVs. Some folks are building what we call piggyback modules that can go alongside of legacy speakers. Somebody wants to convert their current speakers to wireless speakers, then they have this piggyback module that they can hook up to theirs and start moving their speakers around.
And that piggyback module, as Alan showed us earlier, would consist of an amplifier as well as the receiver.
Exactly.
Circuit.
You just wire your speakers right into the piggyback, and you're good to go.
How many products, are there any products available now? And if not, when will we see them?
Right. So we have one of our advisory board members, Aperion Audio, has 2 products on the market today. They have a 5.1 and a 7.1. You can order them today, and they are an online retailer. The expectation, if I can believe what everybody's telling me, all of our members, is that there will be between 15 and 20 products that will roll out between now and the end of the year. I expect CEDIA to be a big, in September in Denver, to be a pretty active announcement period, and then ramping up towards CES in 2014.
Right, right. I wanted to take a look at another couple of the graphics that I have from you. One is called Audio Path, and that just sort of gives us an image of what a WiSA system would look like. You have transmitter devices there on your left. Well, why don't one of you describe what we're seeing here, just for those who can't see it?
Right. I should have brought this up when I had a question about where the D to A converters are and what have you. So on the left side, you have the transmitter devices, and it can be anything from a Blu-ray player to a full-on AV receiver. But it would have that little board that I showed you with the 2 square antennas on it, inside or next to it, or in the front bezel or something, which is what's called the transmitter element in our internal parlays. And that basically just takes the raw audio data out of whatever the decoder, signal processor, what have you, that's inside that device, and then, basically that it basically believes that whatever's after it is a digital analog converter, but what in fact is there is this transmitter element that takes the raw digital audio and then just sends it out over the wireless network.
Now, the transmitter and the whole system really only operates on uncompressed PCM data, correct?
That is correct.
Okay.
That's correct. So the compression clearly adds artifacts, and sometimes it adds latency. And the other thing is that if we had a whole lot more time, well, actually, I may have this visual. That there are strategies for dealing with uncompressed audio that doesn't work with compressed audio. So, for example, if you lose a sample in PCM, there's a way of hiding it really easily.
And we have a graphic to illustrate that too.
Right.
Called error concealment.
Exactly. So it's just a lot easier to deal with the raw data, and of course you get the best signal quality. So so the top is the top line there is, why does it say 6?
I don't know.
Okay, well,
I don't know. I wondered that myself. Every one of these lines starts with the number 6, and I don't know why.
So cool. Yeah. I don't recall seeing the 6 there, but okay. So
Anyway.
the first line is a sine wave pattern that will call whatever goes into the system. So what happens if you don't have sufficient buffering, or if data is lost for whatever reason, a gap could be caused. Okay. And one of the, so all that is that the data would drop out. And usually if the level going out is different from the level at the end, you know, which is kind of at the top of the curve where the red line is, is different from the level of where it starts back again, you'll get some kind of nasty popping or clicking sound, in addition to the gap, which would be a place where there's no audio. So one possibility is that it just, that the data
stitch
is lost
itself back together.
Right. So the top case is that the data is lost altogether. It just forgets about it and then starts playing again at the same time that it left off, which actually is a pretty good idea. But sometimes you get a system that's you know, maybe the developer didn't understand audio, or the networking is you know, trying to do what you do with text, for example, when you get it, where what happens is that it tries to take where the gap is and it tries to smush it together. And so that causes two problems. It causes a loss of synchronization, and you still get the pop.
Right.
Because you see that the glitch is there, but then all the data is early from that point on. So as you gain and lose data, which would be the next line down where you would gain data, that it slips off, and then you've got late data. So if you don't have good latency management, you wind up with this accordion effect where the audio goes faster and slower over time. I don't know if you've
gets ahead of itself and then behind itself over time. Yeah.
Yeah. I don't know, Scott, if you've done any audio editing, but sometimes when you're trying to piece, you know, two takes together, one of them is a slightly different tempo than the other, and this is the kind of thing
very difficult.
Yes. And then, so instead of doing this, if you have PCM data, what you can do is you can send the data out of order. So you take all of the first samples and send them together, and then you take all the second samples. It's like counting off in gym class. You know, all the number ones go to this team, and all the number twos go to this team, and all the number threes go to that team. And so if you lose a packet in this case, what happens is when it's stitched back together, you're just missing one sample in the middle.
And that's what we're looking at in the before concealment line?
Exactly.
Which looks like a kind of a broken up sine wave.
Right, but you still see that shape there, okay? And then the bottom line is what happens if you were to just take those gaps and just connect them with lines. Okay, if you just take a straight line and connect them, which is kind of the most basic way of dealing with this, this is what you get, and you can kind of casually see that it's not looking bad. You know,
but a sine wave is very predictable. An audio waveform is very complex.
Yeah, actually, the sine wave is the one you hear the most errors in this case, because when you put in a straight line, you get harmonic distortion. It's like substituting the sine wave with a square wave.
Right,
Or it's more likely a sine wave with a triangle wave, and you know that those sound different. Now, what instead they do is more like what you'd get with Illustrator. You know, if you ever played with spline curves or what have you, is that they're connected with spline curves instead, and that really drops the harmonic distortion a whole lot. You know, for all types of signals. And yeah, the sine wave is just an example, and if you look at that picture really closely with a microscope, you can see where it's a little bit chopped off in a couple places. And so the lines are used very infrequently because, let me see, here we go. So you start at the red line, count to the right, 1, 2, just the second one after that, you can see where there's kind of a peak, and then it's chopped off.
At
the very top, yeah.
At the very
so
bottom,
where,
yeah.
That's where the harmonic distortion comes in.
Okay.
But if that was done with a spline, it would look impossibly close to the original. It's really very good.
And you're doing and WiSA is doing something on the order of a spline. Then is that what you're saying?
Well, I'm saying that it depends on it's actually an implementation specific thing. We don't test for the sound quality at all.
Yeah, I want to make this one point because this is something that needs to be made very, very clear. The association, and one of the basic tenets starting out was, and as we gathered the original advisory board together, is that we don't want to get in the way of the members' creativity and whatever their secret sauce is, whatever some got great drivers, some got great whatever. And the technology does nothing to get it in the way of that creativity. So whatever they brought to the table originally, but with wired speakers, they can continue to bring that same secret sauce, and we're not going to make them do something that takes them out of their comfort zone, other than putting in an amplifier and receivers or transmitters, depending on what they are, and complying to that wireless link. But other than that, they keep all their secret sauces and whatever it is that they know how to do and whatever they're famous for.
Right. So really, WiSA is concerned only with how well the data gets from point A to point B.
That's right. Exactly right.
And after that, it's up to the manufacturer to do their D to A conversion, you know, their DSP, whatever they want to do.
That's right.
Right.
Got it. Had a question in the chat room here. Wanted to make sure I got to, which was from Alpha 1 Omega. Will this tech work with headphones?
I sure would like it to. It's one of my pet peeves is wireless headphones, and it's something that right now we're really focused on home theater, and we're looking at going into other markets as time permits. Our current priority is to go into more multi-zone arrangements where you would have where you'd be able to go into multiple rooms with this kind of quality, or with your you know, much like you do with an AV receiver right now. And then headphones is a follow-on, and the other we're looking at is commercial industrial. You know, so for performance systems or for community meeting places, what have you, because a lot of times you don't have the ability, you know, for example, in an old church, to go off and run wires all over the place.
By performance, you mean like live concert situations?
Sure. Yeah. The latency short enough that you can actually run monitors on it, for example.
Yeah, I was talking to a guy that works for a company that does just that, you know, rigs for live concerts and so forth. And this is anecdotal, but his comment to me is, you know, we have to run lights anyway, so there's power up on the rack and above. And if I don't have to run speaker wires, I can just plug the speakers in. I can save 20% off the labor cost right then and there. So it's a huge attraction in that market, and in other pro areas as well. So, you know, the associations, we're being drug into the consumer or pro space because they see the immediate value. And so we're working to add that as a market segment that we can concentrate on, have a separate certification program for the pro market.
Man, they would need some serious certification, because, you know, their application is so critical. I mean, if you've got a concert hall with thousands of people in it who have all paid a bunch of money to see this band, you sure as hell don't want anything to go wrong.
That's right. That's right.
Yeah, but look how much wireless is being used right now.
It's already being used. That's right.
And the number of channels, and you know, you've got a RF roadie that runs you know, all the monitors and mics and everything. And
well, that's true. And you've got wireless in-ear monitors, wireless microphones. Right. What are those typically? What frequency ranges are those typically operating at?
They're in the UHF band between 500 and 900 megahertz.
Oh, and that reminds me of a question that came up a little earlier in the chat room. I probably can't find it immediately, but somebody asked about, what about the 900 megahertz band? That's an older band. I remember having a cordless phone in that band many years ago.
Exactly. And then 2.4 came in to replace that. And when 2.4 got busy, then 5.8 got used.
So is 900 just too busy?
900's too narrow.
Narrow, yeah.
For digital. It's actually a really narrow little space.
Yeah.
You know, I don't know. I probably owned 2 900 megahertz wireless headphone arrangements, and they weren't digital. They were FM, and they hissed all the time.
Yeah.
And they popped whenever somebody turned their car on.
Right.
Right.
So that's for analog, and the wireless monitors and microphones being used on stage are also wireless analog, I believe, right?
1 second, my computer.
For the most part?
Stand by just a second.
Oh, okay.
There we go. We went blank here.
Oh.
Did you get that?
So, yeah, I can see you, certainly.
Okay,
So the wireless audio on stage and concerts with microphones and wireless in-ear monitors, is that all analog or is that digital now too?
Some are digital, some are analog.
I gotcha.
Just depends. I think there's more of a move towards digital, and they're able to really pack a lot more in with digital. The prices go way up. Anyway, and there's actually a good chunk of bandwidth there, except the FCC just pulled a big chunk out of the middle of that when they messed up the bands when they shut down analog broadcast. So that's a challenge to people who have older equipment.
Right. Sherlock Holmes in the chat room is asking, can this system get THX certification?
How do you want to answer that?
Uh-oh.
So let me just say that in general, we are working with all of the audio technology companies because they see a trend towards wireless as well, and all figuring out how they can play with the WiSA technology. It's kind of a wishy-washy answer, but so I guess the short answer is there's nothing to keep it from being certified with any of the audio technologies that are out there.
There's actually another general statement that goes along with that, is that we are certainly, again, not looking at quality. So if the consumers are looking for a particular quality standard, then looking to THX would not be a bad idea, for this system. Because it just depends on whether you're how you're listening to it, or if you want somebody else to do the listening and working out what the quality standard is.
That's a good point. THX certification and WiSA certification are sort of two different things, apples and oranges. They're certifying two different things. WiSA is certifying that the data gets from A to B well without problems, and THX is certifying that a product performs up to a certain level of audio or video quality. So the two things could go hand in hand.
I would just say it's more hand in glove than apples and oranges, I think.
Okay, good point.
Yeah.
Okay, final question. I believe that all of your chips and so on, the silicon, if you will, is all being made by Summit Semiconductor. Is that correct?
That is correct. Currently, that's correct.
Are they the only ones that are going to, or are you open to other manufacturers as well?
So at the end of the day, the association, if a company goes out and builds a chip and they sell it to whatever company and they bring a product to us for certification and it passes the CTS, then they're WiSA certified. So from that standpoint, we don't care where the silicon comes from, we don't care where the speakers come from, as long as it passes the certification, we're in good shape. Having said that, I know that I believe that in the future there'll be multiple chip manufacturers out there as well, and I think that's time will tell how that happens and where it comes from.
Also, I was going to just bring up real quick that Silicon Image is one of your founding members, I believe, or one of the original companies anyway. And they are very heavily involved in HDMI, in making HDMI transmitters and receivers and so on like that. Is that what led them to want to be involved in this as well?
Well, I can't speak for Silicon Image. I understand what their strategy is, and their strategy has been all along transmitting high-definition content. Wired, and it looks as though from recent announcements, relatively recent announcements, that they're moving into the wireless space. I think they're one of the members of the Wireless HD Consortium, which is that 60 gigahertz you were talking about earlier. And being able to transmit wireless audio looks like it moves, dovetails right into their overall strategy of moving high-definition content. So I believe that's one of the reasons why they've been very interested in, what happens with the association and the members as well.
Well, Beatmaster in the chat room says an association is only as strong as its members, and it sounds to me like the members of the WiSA Association are pretty strong. You've got a pretty strong coalition starting there, and more companies being added all the time, I'm sure.
Yep. Yeah, we're very proud of the fact that our members have recognized the the oncoming of wireless in general. I mean, and everything's trying to be wireless and turn wireless, and it's just a natural progression that speakers move into the wireless area as well, as long as there is a quality high definition technology that they can adopt. A lot of these guys are looking to move into broader markets using wireless as a means to do that. We all know that there's the spousal approval factor when you're trying to...
I was going to bring that up too, that most spouses do not like wires running all over the place.
They don't, and taking that, and I'm surprised at how big of a factor that was. We were just in Orlando at the Home Entertainment Summit, and this was, of course, at Disney World, and all these guys brought their families, and then they took their wives through the exhibit area, and that was a big thing for them when we said, hey, you don't have to pull wires, and they all of them said, well, we're in. So it is a big deal, and eliminating that, plus giving the audio experience that matches the display, I think there's just, it's a no-brainer. The time's now.
Fantastic. Well, I want to thank you both very much for being on the show. Learned a lot about wireless audio and what to expect in the future. Thank you, Jim Venable and Alan Ruberg, very much.
Thank you, Scott.
Thank you, Scott. It's great.
You bet. You can find out much more about the WiSA Association at WiSAassociation.com. That's WISA Association.com.
Actually,
you can
it's .org.
Oh, it's a nonprofit. Okay.
Yeah, I
Sorry
noticed
about
it
that.
at the bottom of the screen and forgot to mention it.
Oh,
Sorry.
my apology. My apology. WiSAassociation.org. Thank you very much for correcting that, because that's important. We want people to go and see the information, not get lost in the web.
Well, we come up pretty much at the top on Google, so.
Right. Okay. So Google WiSA Association, you'll be fine.
Yep.
Yep.
Thank you very much. You can find me, of course, at avsforum.com and answering reader and listener questions at hometheaterhifi.com. You can also email me if you have any questions at scott@twit.tv, and you can follow me on Twitter at htgeekscott. Next week, my guest geek is scheduled to be Ed Gemmer. Speaking of THX, he's the senior video engineer at THX, and he's going to be talking about the video certification process, including the new 4K video certification. So I'm certainly looking forward to that, and I do hope you will join me. Until then, geek out.